Here we have a typical reaction stoichiometry problem. We've got 2.75 grams of barium hydroxide reacting with an aqueous solution of chromium bromide. Okay, and they give us information about that solution. They are wanting to know how many grams of chromium hydroxide can be formed. So they're looking for the theoretical yield in this instance. Here we've got grams and here's the unknown grams. So it would be very easy when dealing with barium hydroxide to start at mass, to convert to moles, to go through the mole ratio and end up at a final mass of chromium hydroxide. Okay, this would give us a potential value for the theoretical yield. However, there are two reactants. We also have chromium bromide, and we're given this information about the chromium bromide. We're given the volume along with the concentration in molar. And remember, concentration is in itself a conversion factor. So really what we're stating here is 0.534 moles of chromium bromide are found in a 1 liter chromium bromide solution. Very good. But if we look on the wheel, we don't see concentration, do we? But what we know is that concentration itself is linked to the mole. So here I'm going to put it down here. So the calculation where we have chromium bromide at the starting point will start here and it will flow along the same path, giving a possible theoretical yield for chromium hydroxide, Okay, so let's start the calculation. So we've got two reactants. We've got the green route and we've got the yellow route. So if we're going to start on the green route, our assumption for the green route would be that CaBr2 is in excess. This is our assumption. You need to indicate that you're making an assumption. So if that is our assumption, that means we'd start off with our 2.75 grams of barium hydroxide as our starting point. So here we have it over 1. If we've got grams of barium hydroxide and we want to move to moles, we know we need to use the molar mass. Grams at the top to cancel out with those grams. Moles at the top. Okay, 1 mole of barium hydroxide weighs how many grams? And from the periodic table, if we go and calculate it, it's 171.35 grams of barium hydroxide are contained in 1 mole of barium hydroxide. So let's do our cancelling. Both the unit and the label cancel in this case. Now we've got moles of barium hydroxide. We're sitting here. What is the relationship between moles of barium hydroxide and moles of chromium hydroxide? Remember, we get this from our balanced equation. In this case, the ratio is 1 to 1, but you still need to show this scientific logic. You need to show that you know the ratio here is 1 to 1. It might be 3 to 4, it might be anything, but you need to show that you understand that there is a ratio which links the reactant and the product. So 1 mole of barium hydroxide reacts to form 1 mole of chromium hydroxide. Very good. Let's cancel quickly. The unit and the label cancel. The unit and the label cancel. We're on the home stretch. From moles to mass, we know we use the molar mass. 1 mole of chromium hydroxide weighs, and from the periodic table, we found that it weighs 86.02 grams of chromium hydroxide are contained in 1 mole of chromium hydroxide. Finally, on the calculator, to 3 significant figures, we get an answer of 1.38 grams of chromium hydroxide might be our theoretical yield. Now we need to move on to the yellow portion of the equation, and here are our assumption. So we assume the barium hydroxide is in excess. So what is our starting point? We know we can't start with the conversion factor, so we have to start with the volume. We've got 177 moles of our solution, correct? Okay, your chromium bromide solution. Note that this is in liters. Here we've got milliliters. So 1 milliliter is 10 to the minus 3 liters. So if we look at our cancelling here, milliliters and milliliters have cancelled out. We've got liters of solution at the top. That means our next conversion factor must have liters of solution at the bottom. And we know it's 0.534 moles of chromium bromide per 1 liter of solution. Cancel quickly the unit and the label. Here's the unit and here's the label. On the top, moles of chromium bromide. We know we need to indicate that we understand the mole ratio, how the reactant reacts to make the product. And again, it was a 1-to-1 ratio in this example. So 1 mole of chromium bromide reacts to form 1 mole of chromium hydroxide. Cancelling quickly, unit label, unit label. Very good. Final step is the same as the step before. 1 mole of chromium hydroxide would weigh 86.02 grams. Finally, the answer we get is 8.13 grams of chromium hydroxide. So which of our assumptions were true? Our first assumption was true. Our first assumption that calcium bromide is in excess, therefore barium hydroxide is the limiting reagent. And here we have our theoretical yield. Okay, you need to make these 3 final statements at the end of your calculation. This is our theoretical yield, that was in excess, and barium hydroxide was our limiting reagent. So what does this calculation mean? What does this answer mean? It now does not mean anything in terms of the calculation. These two were reference points for each other. So here we have the theoretical yield. This is not the actual yield or the percentage yield. That's something different. Remember, the actual yield is something that we get from real life. The theoretical yield here is the smaller of the two. So for example, if they had continued the question and said, what is the percentage yield if only 1 gram of chromium hydroxide was formed? We know that percentage yield is equal to actual over theoretical times 100 over 1. If the actual yield was 1 gram, the theoretical yield was 1.38 grams, times 100 over 1 would give us a final percentage yield. And remember, we often keep percentages to 2 decimal places, 72.46% yield. So in the laboratory, with human error, with loss of product, we do not hit the theoretical yield. In fact, a percentage yield of about 60% is what's expected in most labs. Anyway, to recap, this calculation is only valid as it stands as a reference point for the statements that we've made. And reaction stoichiometry leans very heavily on the mole ratio. You must be able to show the mole ratio. So in this calculation, here is the mole ratio, which shows your scientific logic. And in this calculation, here is the mole ratio, which shows your scientific logic. Many thanks for watching and best of luck.